Alright, picture this. A squirrel going head-to-head with an elephant in a strength contest and almost winning. Sounds ridiculous, right? That's basically what Vision-R1 7B just pulled off. This tiny but mighty multimodal model scored 73.5% on MathVista, just 0.4% behind OpenAI's O1, which is 10 times bigger. It got there by tackling one of reinforcement learning's biggest weaknesses, overthinking. Most RL-trained models spiral into long, unnecessary reasoning steps, making them inefficient. Vision-R1 fixes this with two clever tricks. First, it builds a massive 200K multimodal dataset without human labels, a process called Modality Bridging. Then, it refines its reasoning with progressive thinking suppression training, which basically teaches it to think efficiently before thinking deeply. Now let's break down how it works.
Vision-R1 is all about improving the reasoning skills of multimodal LLMs. In other words, it's trying to help models that handle both images and text become better thinkers. The authors noticed a key limitation. While reinforcement learning works pretty well for pure text-based models, it doesn't transfer neatly to multimodal models. They tend to struggle with generalizing their reasoning, unless they have really high-quality, well-structured training data. So what's the fix? They propose a step-by-step training pipeline. First, they create a large dataset using an existing multimodal model, plus a tool called Vision-R1, which they introduce here as a system that leverages reinforcement learning to encourage step-by-step reasoning in text-based models. This large synthetic dataset becomes a cold start initialization, giving Vision-R1 a solid grounding in reasoning. Then comes a reinforcement learning phase to refine the model. But if you just plunge straight into RL, the model might overthink and get stuck in inefficient reasoning loops. That's why they introduce progressive thinking suppression training, which we'll call PTST from now on. PTST helps the model gradually develop longer and more complex reasoning skills instead of going all in at once. The result? A model with just 7 billion parameters that can match or even exceed the performance of 70 billion parameter models on certain tasks. Check out the figures here, where you can see how Vision-R1 lengthens its reasoning steps while maintaining high accuracy over time. It's especially intriguing to see the aha moments that Vision-R1 generates. These are points in the reasoning process where the model seems to click into place and figure out the crucial insight. So at a high level, Vision-R1 is about a structured, gradual approach to reinforcement learning, where the model's reasoning skills are built up carefully rather than forced in one go. Let's dive a little deeper. The authors point out that big language models often just skip straight to the answer instead of outlining how they got there, which is fine for simpler tasks but not for complex reasoning. That's why chain-of-thought reasoning has been introduced. Models explicitly write out each reasoning step before giving a final answer. When you bring images into the mix, things get more complicated. Many multimodal models just produce superficial explanations, what the authors call pseudo-chain of thought. It looks like step-by-step reasoning, but it's missing real cognitive processes, such as questioning and reflecting. The paper draws inspiration from Vision-R1, which successfully used reinforcement learning to help text-based LLMs learn to reason independently. They ask, can RL do the same for multimodal models? A direct application of RL doesn't work very well. Why? Because the models simply don't have the right kind of structured training data to develop advanced reasoning. So the researchers propose Vision-R1, a two-phase approach. First is cold start initialization, where they build a huge dataset of reasoning examples by converting visual data into textual explanations. They call that trick modality bridging. Then they fine-tune with reinforcement learning, but carefully, to avoid the model's tendency to overthink. PTST, progressive thinking suppression training, is the key technique, letting the model incrementally grow its reasoning sequences. The big idea is to move away from brute force RL. Instead, they rely on a well-constructed reasoning dataset, combined with a disciplined RL regimen that keeps the model from either rushing to short answers or rambling on with no benefit. Now, understanding images is second nature for us, but it's a real puzzle for AI. That's why modality bridging is introduced here as a core method to help Vision-R1 think in a more structured way about images. Look at figure 3 here. The idea is to turn raw images and text into step-by-step reasoning descriptions that the model can handle. First, the model might generate a simple pseudo-chain of thought from the image-text pair. This includes not just what's in the image, but also why certain details matter, broken down into logical steps. Next, These structured descriptions are refined by DeepSeek R1 before being fed to Vision-R1. Why does that matter? Because if you don't incorporate these structured details, the model might guess or fill in gaps incorrectly. By forcing the AI to articulate visual details in a step-by-step manner, it's much less likely to invent or omit important information. The authors then connect this to broader literature. Step-by-step reasoning is already known to help text-based models, and there are various frameworks like chain of thought prompting or Monte Carlo tree search that can guide AI thinking. But for multimodal models, the question of how to systematically integrate visual reasoning is still wide open. The authors suggest that Vision-R1's approach is a good step toward closing that gap. You might be wondering, why not just rely on reinforcement learning alone to teach multimodal models how to reason? Well, the authors tested that and found it lacking. They tried to train a model dubbed Vision-R1 on 10,000 math problems using RL from scratch. The model was prompted to lay out its reasoning before giving the final answer, in a think first, then answer format. Initially, it looked like Vision-R1 was learning longer reasoning steps, but its performance actually degraded over time. The conclusion is that raw RL by itself doesn't cut it for complex multimodal tasks, especially when data might be messy or limited. This is where Vision-R1 really shines. Rather than going straight into RL, Vision-R1 starts with that cold start initialization on a large, curated dataset. It benefits from modality bridging, converting image information into structured text that can be processed more like typical language data. Then it uses RL fine-tuning to refine those reasoning skills. It's the combination that works. Without a strong foundation, a multimodal model just can't pick up solid reasoning patterns. And if it does, the RL objective alone can cause the model to produce longer answers without genuinely improving the logic. Vision-R1 avoids these pitfalls by splitting the training process into a more deliberate sequence of steps. The authors also noticed a funny thing. Sometimes models generate way too many reasoning steps. That's overthinking. More words don't necessarily mean better logic. So they designed progressive thinking suppression training, PTST, to tackle that. Take a look at figure 4 here. PTST works by gradually increasing the allowed length of the model's reasoning output. Early on, it restricts the model to 4,000 tokens, which is a certain text length. Once the model masters structured reasoning at that shorter length, it's permitted to go up to 8,000, then eventually 16,000. This staged approach trains Vision-R1 to become comfortable with short, efficient reasoning first, then extend it only when it's actually beneficial. To keep the model from spewing out lengthy explanations that aren't helpful, the training uses something called Group Relative Policy Optimization, GRPO, which we'll refer to as GRPO from now on. GRPO balances correctness with structured reasoning. The formula behind it essentially punishes random, drastic changes in reasoning style while rewarding logical consistency and accuracy. By guiding Vision-R1 to build its reasoning skills in increments, PTST prevents the AI from overthinking and keeps its logic tight. And interestingly, Vision-R1 never even needed the longest stage of 16,000 tokens. It learned efficient reasoning patterns well before hitting that point. Let's see how Vision-R1 stacks up against other models. Check out Table 1 here, where it's compared on math reasoning tasks across different categories: geometry, algebra, problem solving, and math word problems. Impressively, Vision-R1 with just 7 billion parameters scores 80.3% on the MathVista benchmark. That's extremely competitive, even next to much larger models. Next, look at Table 2. It shows how often models use self-reflective phrases like wait, mistake, or check. These phrases matter because they indicate the model is pausing to verify or reconsider its reasoning. Vision-R1 Cold, which is the cold start version of Vision-R1, uses these self-check phrases far more often, suggesting it's genuinely engaging with the logic rather than rushing to an answer. Another important detail here is the refined GRPO optimization function. In simpler terms, it's a balancing act. The model is encouraged to produce slightly longer, more thorough reasoning when it helps accuracy, but it's also penalized if it goes off track. The KL divergence term in the formula keeps the model's shifts in reasoning style under control. So all these results boil down to one point. Vision-R1 doesn't just guess answers, it learns to think through them. And that's why it does so well on these benchmarks. More benchmarks, more insights. Table 3 here compares Vision-R1 with other top AI models across a wide range of tasks. Not just math, but also general reasoning and comprehension challenges. Vision-R1 again shows strong performance, demonstrating that its reasoning skills aren't limited to any single domain. If you're curious why Vision-R1 is good at striking that balance between depth and accuracy, check out Table 4. It breaks down the impact of different training methods, things like cold start initialization, GRPO, and PTST, on the final performance. One metric is the average token length. With PTST in the mix, the model's reasoning chains get longer only as much as needed, ensuring it doesn't produce extra fluff. All of this indicates Vision-R1 generalizes well. It can handle various types of reasoning tasks without resorting to rote memorization or superficial answers. It's not just about math anymore, the approach works broadly. Now for the fun part. Actual examples that show Vision-R1 thinking like a human. Take a look at Figure 5 here. You'll see real geometry problems taken from the MathVista benchmark. These aren't trivial tasks. They require the model to parse geometry concepts, angles, tangents, parallel lines, you name it. The first example shows a problem about parallel lines and bisected angles. Instead of just stating the final answer, Vision-R1 breaks down each step. It identifies how the angles are related, does the math, and then confirms the answer matches the given options. In the second example, there's a tangent and radius problem. Vision-R1 remembers that a tangent to a circle is perpendicular to the radius at the point of tangency, so it applies that 90-degree rule. And again, it double-checks the final result rather than just spitting it out. The third example is especially interesting. The model tries one method first, gets an answer, then says, wait, let me try a different approach. It's basically verifying its own work. This kind of self-reflection, where the model cross-checks solutions, is what the authors call an aha moment. It's a sign that Vision-R1 is doing more than pattern matching. It's reasoning in a way that's reminiscent of how humans tackle problems. That wraps up the main idea. Everything. Vision-R1 combines structured training data, careful reinforcement learning, and progressive thinking limits. The result is an AI that reasons step by step and can even pause to question itself, making it an exciting approach to multimodal reasoning. Thanks for joining us today. Happy exploring!